So now we want to introduce, or at least reintroduce, the ideas of potential energy, do some examples with those, and then talk about energy conservation. So again, with potential energy, we have two types. We have gravitational, and we have elastic. And we typically write gravitational potential energy as mgh, and we write elastic potential energy as 1/2 kx squared, where again k is the spring constant and x is the distance the spring has been stretched from equilibrium. Well, let's start with gravitational. So suppose we have some ground and I have a brick, and that brick can have some mass. Let's say the brick is 10 kilograms. Okay? And let's say that I've lifted the brick some distance above the ground to a height of, for kicks and giggles, let's say 10 meters. Okay? Now, in lifting the brick, I've done work to the brick. So, by our previous video, I input some energy into the brick. As I was lifting it up, that brick was gaining kinetic energy. And then when I leave it up here, okay, that energy didn't just disappear, it went somewhere, and where it went was into potential energy. Okay, and so potential energy is, again, the type of energy that an object has, stored energy, if you will. It's the energy that an object can do work with if that energy were to be released. So how much potential energy does this object have? Well, we'll just multiply everything through, and the mass is 10 kilograms, and gravity is 10 meters per second squared, and our height is 10 meters, and so we've input 1,000, and I think one thing I forgot to mention last video was what the units of energy were. Okay, so here we have a kilogram, and we have a meter per second squared here, so this would be a Newton. mg, remember, is the weight of the object, so that's just a Newton, times meters, so that gives us a Newton meter, and that's, again, the same thing as work. So energy, all energy, kinetic, potential, all have the same unit as work, and they're all in joules. So we've given this object 1,000 joules worth of energy, potential energy, okay? Now here's a question I might ask, okay? Well, let's go back to the previous slide. If we let the brick go, what will its speed that it hits the ground with? With what speed? With what speed will it hit the ground? Okay, now to answer this question, we have to invoke a principle, one of the most sacred principles in all of physics, and this is the law of energy conservation. Now, what this means, what energy conservation means, okay, you may have heard the term conservation law before, but what it means is that there's a quantity that doesn't change. Okay? There's a quantity that doesn't change, and in this case, it's the energy. Or more succinctly, the total energy. So for our purposes, the total energy is going to be equal to the kinetic energy of an object plus the potential energy of an object. There are a few other types of energies, namely thermal energy, but we don't worry about that in mechanics. So the total energy that an object possesses is just going to be its kinetic energy plus its potential energy. Now, energy conservation holds, okay? Energy conservation holds when we can neglect frictional forces. Okay, energy conservation holds when we can neglect frictional forces. Right? So things like normal friction, books sliding across a table, or air resistance, anything like that, we tend to call those dissipative forces. Okay, they dissipate energy out of a system. And when we can neglect those, when we can ignore those, then this idea of energy conservation holds. And so energy conservation says that the total energy in a system is going to stay constant. Okay? Now, the amount of kinetic energy can change and the amount of potential energy can change. They can change from one to the other, but their sum will always be this total energy E. So if we go back to this diagram that we have here, what this is saying, what energy conservation says, is that the initial energy in the system, the total initial energy in the system, must equal the total final energy in the system. Okay? So total energy initially must equal the total final energy. And so here we know what the potential energy is initially. We know it's 1,000 joules. But what about initial kinetic energy? Well, it turns out that it's 0, because if I'm holding it at rest before it falls, then its velocity is 0, and hence its kinetic energy is 0. So for this particular situation, before the brick falls, all energy is potential. Okay? So that means that EI, in this case, is going to equal PEG, initial, right? And when it falls and hits the ground, once it hits the ground, all right, let's go back. Whoop, too many slides. Once we come back, after the brick has hit the ground, right, it's hit the ground and it's made a loud thwack, then its height is no longer 10, its height is now 0, and so its potential energy is 0. Okay? So that means all of the energy has been converted into kinetic energy. So its final energy is going to be converted completely into kinetic. Okay? So another way to write this, if you want, would look like this. The initial gravitational potential plus the initial kinetic must always equal the potential final plus the kinetic final. But in our case, okay, and this is only in our specific case, In our specific case, there is no initial kinetic energy, and there's no final potential energy. So we're just left with this. And so, if we want to know with what velocity it was going to hit the ground with, now all we have to do is solve this equation for v. And we know how to do that because P, our potential energy, is mgh, and our kinetic energy is 1/2 mv squared. So now all I have to do is solve for the v, and notice something very peculiar. Our m's are going to cancel out. So this is a little striking. A 1 pound brick is going to strike the ground from 10 meters up with the exact same velocity, neglecting air resistance, that a 15-pound bowling ball will. Okay, so mass does not matter. As long as air resistance is negligible, mass does not matter. So, continuing to solve, we'll multiply both sides by 2 to get rid of the 1/2. So we have 2gh, v squared equals 2gh, and then we'll take the square root. And so we notice that our velocity is going to be the square root of 2gh. So in this case, it's going to be 2 times 10 meters per second squared times a height of 10 meters. And this is going to be 2 times 10 is 20, times 10 is 200. The square root of 200 is going to be right around 14.14 meters per second. And that's the speed that it's going to hit the ground with. Now I want to contrast that situation, okay, maybe drive this point home a little bit more. Contrast that situation with the situation where we have a block sitting on the table, and we pull with a force in this direction, but there's a frictional force in this direction. Okay? By the example earlier, we saw how to determine what the change in kinetic energy would be of this block if we knew what the force was and if we knew what the mass was, as long as friction were negligible. But in this case, if friction is present, okay, then it's going to slow the acceleration down, and so the change in kinetic energy is not going to be a true representation of what the overall work done was. Okay, the work and the change in kinetic energy will not necessarily, well, the work and the change in kinetic energy will be the same, but energy conservation doesn't hold. The total amount of energy in the system will not stay the same. Okay, so I wanted to make that point very clear. So now let's look at elastic potential energy. And elastic potential energy has to do with springs. So let's say we have a spring here, and this is its equilibrium length. We'll denote that as L sub I. Okay, and let's say we attach a block to the spring and then compress it this way. And we now have a new length, just L. Okay, so we have this length right here that the spring has been compressed. Okay, so from here to here, this length X, the spring has been compressed. So we have put a potential energy into the system. If we hold the block in place, nothing will change, but if we release the block, then the spring will push it out and it will move out at some initial speed. And we can actually calculate what that speed will be. We'll do that here in a bit. But for now, okay, again, the PE is going to be 1/2 kx squared. And I want to talk a little bit about what this K is. Remember that K is the spring constant, and K determines the stiffness of the spring. Okay, K determines, I can't make a K for the life of me. K determines the stiffness of the spring. Okay, so the higher the spring constant, the more stiff the spring. Okay, so something like a slinky is going to have a very low spring constant, whereas the shocks on your car are going to have a very large spring constant. Okay, so let's just do a quick example here and see how to use conservation of energy in spring systems. Let's say that our block here is 2 kilograms, and our spring has a constant of 12 newtons per meter, and that's the units of the spring constant, newtons per meter. And we compress the spring. Let's say 10 centimeters, which is equal to 0.1 meters. Okay, so if we compress the spring 10 centimeters and our spring constant is 12 and our mass is 2 kilograms, what we can ask is, what is the actual elastic potential energy, and if we let it go, what will the velocity of the block be right as it passes through its equilibrium point? Right? What will the velocity be at this point if the block is let go? Okay, so let's first calculate the potential energy. So this is going to be 1/2 times 12 newtons per meter times 0.1 meters, quantity squared. So 0.1 squared is going to turn into 0.01. 12 newton meters times 1/2 is going to be 6. So 6 times 0.01 is going to be 0.06 joules. Okay, so we've given this object 0.06 joules. Now, if I want to calculate the velocity at equilibrium, equilibrium means that our x value is 0. And hence, no potential energy. So as the block is sprung forward and it moves through the equilibrium position right here, at that specific point, all of the energy is now kinetic. So at equilibrium, all energy is now kinetic. And if we assume that the surface the block is moving on is frictionless, all we have to do is set up our conservation of energy equation, which says that our energy initial is equal to our final energy, and in this case, our initial energy is the elastic potential, and that must equal our kinetic energy moving through the equilibrium position. And here we see that our masses don't cancel out, so things aren't going to work out quite so nicely for us, but we can get rid of the 1/2s. Okay? And to continue solving for v, I divide both sides by m. And then I take the square root. And because this is the square root of k over m times x squared, sometimes people write it as x times k over m. Okay, so if we do this, okay, this is going to equal, I'm going to write this up here, 0.1 meters times the square root of 12, and I'm going to drop the units for space sake, but know that the units are still there. 12 over 2, so this is going to be 0.1 times the square root of 6, and inside here we're going to get essentially 1 over seconds squared is the units we're going to get in here. I won't work through the units, but that is what you get. And so the square root of 6 is approximately 2 point something, which is right close to 2.45 meters per second. So that's, we need to multiply that by the 0.1. So this is actually going to be 0.245 meters per second. Okay, so the block is going to move through the equilibrium position at a speed of 0.245 meters per second, or right around 25 centimeters per second. Okay. Now, to finish out our conversation of conservation of energy, I want to point out one more example. Okay, I want to point out one more example, and that is, think of a block sliding down a ramp. A block of mass m, and it's sitting at a height h above the ground. Okay? Now, one classic problem in physics is to calculate the speed of the block at the bottom of the ramp if the ramp is frictionless and we know how high the block is. Now, we can do this with two methods. We can either use Newton's kinematic equations or we can use energy conservation. But again, if we were going to use Newton's equations, we would have to know the total length that the block was going to slide down, and we would have to know the angle that the ramp made with respect to the ground to calculate the acceleration, because things sliding down inclines don't accelerate quite as fast as falling objects do. So the acceleration due to gravity is modified by this angle here, and we would have to solve for the acceleration using a known trigonometric property, and then we would have to find the time, and then we would have to find the velocity, and it can get pretty hairy pretty quickly. Or we can use energy conservation, which says the initial energy, or the energy where the block is up here, must equal the energy at the bottom of the ramp. So if we release the block from rest, then all the block has initially is potential, and at the bottom all it has is kinetic. And again, we've already solved this problem, so you already know how to do it. The final answer is just going to be the square root of 2gh. And this is in fact the answer that you get if you use Newton's methods, but it takes quite a while to get there, or at least it takes longer to get there than here. So whatever this height is, as long as you know what the height is, you don't have to worry about modifying the acceleration due to the ramp. And this brings up a curious thing. Okay? If I have a block sliding down a ramp, and I release a block from the same height above the ground, both hit the bottom, or the ground, at the same speed. Now, yes, this block hits first, and this block takes longer, but they both end up hitting the bottom at the same speed. Now, this process can also work in reverse. All right, so imagine you're on a skating rink, so here's a bunch of ice. And here's a frictionless hill. And you have a box. And you push that box, you give it a nice shove, and if you just give it a nice shove, then the box will not slow down because the surface is frictionless. Or you can think of a hockey puck or something like that, and it will move along until it hits the hill, and then it'll move up. And it'll move up until all of its kinetic energy has been converted to potential energy. So in this case, if we wanted to find how high up the hill will the box go if we knew its initial velocity, and let's just say that the initial velocity was 2 meters per second, just for kicks and giggles. Okay, so if the initial velocity is 2 meters per second, how high up will the box go on the hill before it starts to slide back down? And here again we can use conservation of energy because everything is frictionless, and in this case our initial energy is kinetic. And our final potential, or our final energy, is potential energy. And again, the masses go away. And this time I'm solving for the height. So the height, I just divide by g, both sides by g, and the height's going to be v squared over 2g. So this is going to be 2 meters per second, quantity squared, over 2 times 10 meters per second squared. So this is going to turn into 2 over 10, essentially, or 0.2 meters. That's how high the box is going to go. Obviously, if you hit it like a hockey puck would be hit, it'd be going several meters per second, maybe upwards of 30 or 40 meters per second. For a good, decent slap shot, some can be hit even harder than that. The higher it's going to go, obviously. But the situation can work in reverse. So to sum up, for conservation of energy, use EI equals EF, and then determine what initial E is. Is it potential? Is it kinetic? And then step 3, determine what final E is. Is it potential or is it kinetic? And then 4, solve for whatever variable the problem asks you to, and then plug in values. So it's a very easy recipe with which to attack a multitude of problems. It's one of the most useful tools in all of physics. So it'll be one of the most useful tools in all your mathematical tool belt. Okay, so that is it for conservation of energy. Next up will be momentum. We'll see you then.